Welcome back, good morning. Today we will discuss and prove a very important result in queuing theory known as Little's theorem. So, Little's theorem relates the average number of customers in a queuing systems to the average waiting time in the queuing system. Roughly it says that average occupancy is equal to average arrival rate times average time spent in the system. Okay, so, this is roughly this is the intuitive, is what it says, right. So, average we have to make precise what we mean by average occupancy, average waiting time, etc., average time spent in the system, etc., right. This is so the way you prove this is using renewal reward approach. In particular, we have to use the renewal picture we put out yesterday. We said that in GG1Q we looked at FCFS, but this is not just only for FCFS. We said that consecutive arrivals to an empty system constitute renewals, right. So, in this picture, if you look at this picture that I have drawn, this black step function is the arrivals, right. There is an arrival at 0, right. The system starts at 0, then there is an arrival to an empty system, and then this black step is basically denoting the arrival process A of t, which is n of t plus 1. N of t is the renewal process of arrivals. Okay. And these are distributed as some xi, okay. And service times are distributed as vi, okay. These are IID and xi's and vi's are independent, okay. Now, I have drawn the black step is, as I said, the arrival process, and the blue curve is the departure process. So, at any given time t, A of t denotes the total number of arrivals that have come to the system, and D of t denotes the total number of departures from the system, right. So, if I were to, so these are your, so this is your little x 1, the realization of x 1, this is x 2 and so on, and this is your V naught. Now, the renewal instances are, can you mark in this? So, this is the 0 of course, is an arrival to a empty system, right, and then this arrival, if you look at, that is an arrival to an empty system, right, and then that is an arrival to an empty system, right. So, these purple crosses are arrivals to an empty system, correct. So, in the picture the 1 2 the third arrival, right, this is x, this is the epoch of the third arrival, and this one is the epoch of the fifth arrival, is not it. So, this is the subsequence which sees empty system, right. So, we said yesterday that this subsequence of these arrivals which see empty system constitute renewals, right. So, what we are saying is that these durations and similarly subsequent arrivals to empty systems are IID basically, right. So, we can denote these by x 1 r, x 2 r, this is a different notation. So, this is the inter renewal periods of the the subsequences with subsequences, right. So, these are renewal instances. I am putting R to distinguish them from the arrival process, which is also renewals. Arrivals are x1, x2, etcetera. This x1R, x2R, etcetera are these durations between arrivals to empty systems. Okay. And each of these renewal intervals constitutes one busy period, after which there is some empty time, and then there is a busy period, and then there is some empty time. Okay. So, this x1R itself has a busy period till this point, right, till this point from 0 till this red dot is a first busy period, and likewise from the first renewal to this red dot is a busy period, right. So, this is a busy period. So, each of these XIRs constitutes one busy period followed by some empty time, and then there is another arrival to an empty system which constitutes a renewal. Okay. We use stopping rule, the tool of stopping rules to prove that these are indeed renewals, these XIRs are indeed renewals, and we can also show that the number of arrivals during any of these renewal periods are also IID. Okay. So, essentially each of these busy periods followed by some idling, if you look at these renewal intervals, they are all statistically identical copies of each other. Okay. That is the key thing to note. Okay. And this is very general, okay, that this renewal aspect, that the renewals to empty systems constitute arrivals to empty system constitute renewals is holds regardless of FCFS. It even holds for GGM, you could have even multiple servers. When the system finally empties, when there is nobody in the system and there is a new arrival, consecutive such instances are renewal intervals. Okay. So, this is what we will use, okay, for Little's theorem. Now, what does Little's theorem say? As I said very colloquially, I said that average occupancy is equal to average arrival rate times average time spent in the system, right. Now, what is the average occupancy? So, at any given time t, okay, so the number of customers in the system at time t is equal to what? Let us say L of t, okay, is equal to what in this picture? It is the total number of arrivals minus total number of departures at that time, right. Everybody who has come so far minus everybody who has left so far will be the number left in the system, right. This could be, this is some non-negative integer, this could be 0 or any integer, right. Is it clear? So, what is the average occupancy of the system? Now, the question is, are you talking about ensemble averages or time averages, right. For you would expect that if the Q is ergodic, it should not matter, right, but since we have studied time average rewards so far, we will look at time average occupancy. Okay. So, average, let me say time average system occupancy is equal to what? This guy, limit t tends to infinity 1 over t integral 0 to t L tau d tau. Okay. Now, the question is, does this even exist? I have just written out some limit t tending to infinity 1 over t integral 0 to t L tau d tau, right. There is no reason to believe that this limit exists, right. It is not clear. See, what you can argue is this L t L tau is a legitimate reward function if you look at the renewal process defined by x1r, x2r and so on. These renewals at arrivals to empty systems. If you take these purple intervals in my picture x1r, x2r as the underlying renewal process, we can argue that this L of tau is a legitimate reward function for this renewal process. Namely, at any given time L of tau depends only on the x random variables and v random variables in that busy period, correct, that busy period whatever that renewal period, right. Therefore, if you take L tau as a reward function for the renewal process defined by x1r, x2r and so on, then by renewal reward theorem this time average will exist, and in fact we know what it should be equal to almost surely, right, should be the expected reward over a renewal interval over expected renewal duration, all right, and the expected renewal duration is simply expected x1r or expected xir in general, right, all right. So, this is the this is the approach we will use renewal rewards. Okay. So, what is if you take some time tau, right, let us say I take some time tau out here. Okay. What is integral, what is this integral? Sorry, I should say I take some time t, I guess, right. Let us say I take some time t, what is this integral 0 to t L of tau d tau? See L tau is simply a tau minus d tau. So, and the integral from 0 to t will simply be the area between the a and the d curves, correct. So, this integral that I have circled in green will simply be that bit, right, till t you have to integrate out and get that area, right, and divide by t. Now, it is actually easy to see what this area is within a renewal interval, right. So, for if you look at the sum of these areas in green, right, what is, so this is all this is all a jump of 1, right, each time the jump is 1, right. Now, what is this width for example? Remember sir, this is the entry time of that x1 customer, the first arrival after 0, and that person exits here, right. So, this is simply what? It is not the waiting time is it is not the WQ that we considered yesterday, it is the W. So, this guy will be W1, correct. Likewise, if you look at this width will be, so this is where the x2 customer enters and this is where he leaves, right. So, this will be W2, right, the total time spent in the system by that x2 customer, right, the second customer after 1. Now, okay, please keep in mind that this W1, W2 are different from the W1Q, W2Q considered yesterday, and when we are talking about the average time spent in the system, we are talking about not WQ, but W, okay, is that clear? So, to get back to our question, so of course, this V naught is equal to the time spent in the system by the 0th arrival, right. So, what is this area under this green, what is this green area? The width is the Wi's and the height is 1, right. So, the total area within a renewal interval is the sum of the waiting times. So, not the waiting time, sum of the W's, right, so system times, correct. So, there you see a relationship directly, right. So, the integral 0 to t of L of tau, which is the L of tau is the system occupancy. If you integrate that till some time, it looks like you are adding the waiting times of all the customers you have seen so far, and therein lies the fundamental relationship, okay. And this relationship will hold it really has nothing to do with first come first serve or last come first serve. Okay. This is a fundamental relationship. The picture will change for some other service time, but this relationship will hold. So, let us look at this a little more closely. So, you can look at, so let us say you look at this, right, what is integral 0 to this instant is let us say S1 r and this is S2 r, right. These are the epochs, renewal epochs of this purple process, right. Now, what is integral 0 to S1 r of L tau d tau? It is simply the sum of W I, right. See, j is the index of the first renewal arrival to an empty system, right. So, it is really I is equal to 1 to j minus 1, where j is from yesterday, right. So, where j is the, you have to recall from yesterday, minimum n such that sum over j is equal to 1 to n x j minus v j minus 1 greater than or equal to 0, is that right? This is, what is this equal to? You are just integrating the reward over one renewal interval, right. So, this is like your R n, so to speak, R 1 this is, right. We will call this L 1. Similarly, L n will be integral over the nth you know from S n minus 1 r to S n r or whatever, right. But they are all IID. The issue is that L n defined like so, this is the definition for L 1 for the first renewal duration, but you can define an L n similarly and these L n's will be IID, correct, and that is the key issue, right. If you have that, if these L n's are IID, then you will actually have Little's theorem, that is the point. Okay. Actually, we can write this in a slightly different notation too. We can write this as sum over I is equal to 1 to let me get this right, n of S1 r minus 1 of W I. Okay, this may look like complicated notation, but it is really not that complicated. So, S1 r is this guy, this, right. So, n of S1 r is the index of the first arrival to a empty system, n of S1 r minus 1 is the arrival before this, right. So, you are adding all the waiting times of the arrival, just of all the arrivals till just before the arrival to an empty system, correct. So, that is why I put a n S1 r minus 1, right. So, n S1 r is your j if you think about it, right, it is exactly your j, right, it is the index of the arrival which sees an empty system, and likewise you can define L n. Okay. I think I made a small notational mistake. If you just go back, the first customer has waiting time W 1 in my notation, this is it, can you confirm? Yes. Yeah, so then I made a small mistake. So, I should just write W 2 over here and W 3 over here, okay, then I will be okay. So, W 1 includes your 0th customer, that is all I am saying. So, and then this will be okay. Thank you for pointing out. Now, we are okay. So, I think there was I was off by 1 basically, now we are okay. So, this is great. So, I would expect this, right, if renewal reward works out for this big renewal process, this purple renewal process, we expect this limit t tends to infinity 1 over t integral 0 to t L tau d tau should be equal to expected, can you tell me, expected what, L n, right, or L 1 does not matter, expected L 1 over expected renewal duration, which is x I r, which is I can just write x 1 r almost surely. right. So, if you regard L of tau as a reward process for the big renewal process, by big renewal process I mean this purple renewal process constituting arrivals which arrive to an empty system, then we have this 1 over t integral 0 to t L tau d tau, this limit as t tends to infinity, this time average exists almost surely and it is equal to this guy expected L 1 over expected x 1 r, okay, almost surely. Okay. And if your expected x is greater than expected v, meaning that the queuing system does not build up forever, then this will be something finite. Okay. So, great. So, this number exists, right. So, this is what I am going to call, this number I am going to call my L bar. Okay. What is L bar? Time average system occupancy. Okay, which is the time average number of customers in the system. Okay. So, this L bar exists. Okay. Now, we want to prove that this L bar is equal to average arrival rate times average waiting time or the system time in the system, right, time spent in the system. So, that is what we will prove, okay, using this relationship about the integral of L and the sum of W's. Okay. So, if you look at this picture, for any time t, the integral from 0 to t is simply the sum of the W's of the customers who have left so far plus maybe a little bit, right, of people who have been waiting so far also, right, which is this bit here. So, I will use a bounding approach as usual. Okay. So, what will I really do? I will basically take this 1 over t integral 0 to t L tau d tau, which is the area denoted in green here, is lower bounded by the sum of all areas till the previous renewal interval and upper bounded by the sum of areas till the next renewal interval. So, that is the relationship I am going to use. Okay. So, I am going to say that, so this is from the picture, okay. We have from the picture itself you can say, so integral 0 to t L tau d tau is lower bounded by sum over n equals 1 to n r of t of L n and it is upper bounded by so, L 1 is the this green area under the first renewal period, right. So, if I go from integral 0 to t, right, L of tau, it is lower bounded by the sum of areas of these W's, right, it is lower bounded by L 1, right. So, in general if t is somewhere in some renewal interval, you sum all the green areas till before that renewal interval, you will get the sum over L n's. Okay. So, n r of t is the, I am counting the big renewals now, the purple renewals, n of t is the renewal arrivals, n r of t is the underlying renewal process of these arrivals to empty systems. Okay. So, this is just looks like extremely complicated notation, but it is really just saying that this picture. Okay. If you just have this picture, you will be okay, alright. And I am upper bounding it by, so this area under green is upper bounded if I were to go to the next renewal interval, that is really all I am saying. Okay. So, if you then take 1 over T, again, so I may be off by 1 here, I think, sum over W I, W 1 is the waiting time of the first, this is the n of t, this might be n of t, I think. Okay. I think this includes the n of t arrival. Okay. This n of t is the you know the arrival process, n r of t is the renewal process. Okay. There are two renewal processes here, so it may be a bit confusing. There is a renewal process of arrivals and there is a bigger renewal process of arrivals to empty system. I have R for the bigger renewal process, so to speak. Okay. So, but this notation is really complicated, but the picture is very intuitive, right. So, if you look at 1 over T of this, so if I take limit t tends to infinity, integral 0 to t L tau d tau over t. So, this will be, so you can basically put 1 by t throughout in the previous equation, right. So, the question, this will actually be equal to 1 over t sum over I is equal to 1 to n of t W I. Why is that? Because this is upper bounded by 1 over t of you know the sum of areas till the next renewals and lower bounded by the corresponding sum of areas till the previous renewal. Okay. And this average we know goes to this, we know goes to this is almost surely equal to what, expected ln, right, over or expected L1 over expected, yeah, I can just write x, all these Li's are identically distributed, expected L1 over expected x1 r, okay, because I am using sandwiching, right, because the sum over Wi is sandwiched between these sum of these Li's, right. So, here also there is a limit. Okay. So, this is your, this is of course your L bar which we have already defined, right. Now, the question is what is this equal to? Here I can write it as limit t tends to infinity, I can multiply divide by n of t, n of t over t times 1 over n of t Wi. What have I done? I have just put n of t multiplied and divided by n of t, right. Now, this guy is very well known to us. What is that equal to? N of t, remember, is the arrival renewal process, right. So, n of t over t goes to 1 over x bar, which is lambda, right. Okay. So, I am going to write this as follows. So, this is equal to limit t tends to infinity n of t over t, okay, times limit t tends to infinity 1 over n of t I is equal to 1 to n of t W I, correct. This is equal to the lambda, right, which is just 1 over x bar, right, this lambda is just 1 over x bar times this is equal limit t tends to infinity, sorry, limit t tends to infinity n over n of t sum over I equals 1 to n of t w I. Now, what is this equal to? If you look at any ideas. So, this is 1 over n of t sum over I equal to 1 to n of t w I, which is the you are adding all the system times of customers who have showed up till time t, dividing by total number of customers who have showed up till time t, right. What is that equal to? Average time spent in the system. Now, see, there is no, as such there is no reason for this limit to exist, right. If I just tell you that there is this limit t tending to infinity of 1 over n of t sum over I equal to 1 to n of t w I, right. So, we know that n of t goes to infinity, right. So, this is like, so whatever is in this box is like this limit, right. If I just send you limit n tending to infinity 1 over n sum over I w I is equal to 1 to n, right. This is just the average system time, right. There is no reason for this limit to actually exist as such, right, but because of this relationship between L bar, see L bar exists, right, almost surely this integral 1 over integral 0 to t L of tau d tau over t goes to an almost sure limit L bar, right, and of course, limit t tends to infinity lambda n t over t goes to lambda almost surely, right. Therefore, what remains must also go to a limit almost surely, right, correct. So, what does it show, right. So, therefore, so this implies that limit t tends to infinity 1 over n of t 1 to n of t w I, which is simply limit n tending to infinity 1 over n I is equal to 1 to n w I, this limit must exist. Correct, and this is your, so this is your average. So, if this guy is your average time spent in the system, okay. So, say equal to w bar, right. So, what have we proven? So, we have proven L bar is equal to, okay. So, again just going back and looking at this, yes.
How did the inequalities become?
So, I will tell you how that happened, right. So, how did I make this equality, right, that is the question. So, if you look at, so there is this inequality here, right. So, 1 over t integral 0 to t L tau d tau should be less than or equal to 1 over t of all this, right, but then if I put 1 over t here in front of this, so if I put 1 over t here, right, and 1 over t here, right, 1 over t throughout, now send t to infinity, this guy and this guy will go to the same limit, because they go to the same limit L bar. So, by sandwiching the limit will become equal, is that clear. So, maybe I should do this. So, what I am saying, yeah, you put 1 by t everywhere, right. So, this is 1 over t 1 over t 1 over t, okay. This the upper bound and the lower bound will both go to expected L 1 over expected x r x 1 r. Therefore, limit t tending to infinity of the integral will be equal to limit t tending to infinity of sum of the w i's, okay. And then we are saying that we are just multiplying dividing by n of t by t goes to lambda, we know that strong law, right, and then this beast, right, this beast that I have circled out here will have to go to a limit almost surely, will have to. Why? Because left hand side is having an almost sure limit and n of t over t has an almost sure limit. So, it cannot be that, it has to be the case that 1 over n of t sum over I and sum over I equal to 1 to n of t w I must have an almost sure limit, and that is your average system time, right. This is average time spent in the system by a customer. You are taking the sum total of all system times and dividing by total number of customers, right, that is your average waiting. Is that clear? And if you see what is the crucial element in this, FCFS is not at all crucial, okay. FCFS is only for the picture. If it is a last come first serve, your picture will be different, but the relationships will still hold, okay. So, if FCFS, the service discipline is not at all relevant. In fact, even GG1 is not very important, you can do GGM also. Even if you have M servers, consecutive arrivals to an empty system will still be a renewal durations, and we can still use the same sort of a mechanism to work it out, okay. Even for GGM, Little's theorem will hold, okay. See, of course, the value of L bar and W bar will be different, but when I say Little's theorem holds, I mean that L bar of that system will be equal to lambda times W bar of that system. So, even if you go from FCFS to some other discipline, LCFS let us say, the L bar for FCFS could be different from L bar for LCFS, alright, and W bar for LCFS will be different from W bar for FCFS, but nevertheless the equation lambda bar equal to L bar is equal to lambda W bar will hold, that is what I am saying. See, when I say service discipline is not relevant for this to, I mean it is not crucial, I am not saying that everything will be the same, I am saying that the relationship L bar is equal to lambda W bar will still hold, lambda bar will be different across different service disciplines, okay. Generally L bar and W bar will be different across different service disciplines, okay. Is that clear? So, this is Little's theorem, okay. We can also apply Little's theorem to just the server, okay. So, you have this GG1 queue with a server, right, you have arrivals, people queuing up and all that. What you can do, you can just put the server let us say inside a box. Now, if you just look at the server, okay, the server will see how many people can be in the server, either 1 or 0, right. So, if the server is serving one person, that person finishes and immediately the next person comes, there is no gap, right. So, it will serve one person, that person ejects, another person comes, it will serve, eject, and then it will become empty at some point, right. So, now again we can argue just looking at the server, consecutive arrivals to an empty server, which means consecutive arrivals to an empty queue, the server is empty only if the queue is empty, right. So, consecutive arrivals that come to an empty server also again of course are renewals, right. So, we can use the same sort of argument to get a Little's theorem for the server, okay, same argument, okay. So, expected you can say so what is this, right, not expected, let us say time average. Time average number of customers at the server is also the time average fraction that the server is busy. Because time average number of customers at the server is just see number of customers is just 1 or 0, right. So, time average of that will simply be the fraction of time that the server is busy, because it is just between 0 and 1, right. I mean it is either 1 or 0, and the time average number of customers in the server will simply be the time average fraction that the server is busy. and this will be equal to what? Arrival rate lambda times average time spent by a customer at the server, right, which is equal to what is the average time spent by a customer at the server? Yeah, 1 by average time spent by the customer, right. This is lambda times expected V, right, which is simply lambda upon mu. Okay. Okay. So, the fraction of time that a server is busy is simply lambda over mu, okay. And the time this fraction of the time that the server is busy is denoted by rho, okay. This rho is called the load on the system, okay. Load simply denotes what fraction of my time is my system busy. System busy means server busy, right. So, we get rho is equal to lambda over mu, it is the arrival rate over service rate. This is another very fundamental relationship in queuing systems, that the fraction of the time that the system is busy or the server is busy is equal to average arrival rate over average service rate. Okay. This is again not just true for GG1 FCFS, it is true pretty much across the board, right. All you need is arrivals to an empty system must be renewals, that is all that you need, then this is true. Okay. Okay. Then you can just subtract. So, now if you look at L is equal to lambda W bar, what is L bar minus rho? See, L bar is the total number of customers in the system, rho is the fraction of customers that I mean see L bar is the average number of customers in the system, rho is the average number of customers at the server. So, L bar minus rho will be average number of customers who are waiting at the queue, right. So, you can subtract these two and get LQ bar is equal to what? Lambda is the same, lambda times W bar minus 1 over mu, correct. What is W bar minus 1 over mu? W bar is the total system time, right, 1 over average total system time, 1 over mu is the server time, right. So, this is equal to lambda W q bar, correct. Okay. So, if you just look at the buffer alone or if you just look at the server alone, some a little theorem holds for them separately also. Okay. So, this is very powerful. So, you look, so even if you are given some very complicated queuing system, you can just look at some part of it, right, and apply little theorem for that part. Okay, even if you are given multiple queues, as long as there is no correlation between arrivals and all that, then you can still apply little theorem. It is very general and powerful. Okay, I will stop here.